What I would advise for the approach to that one is that you start out and you solve for the magnetic field as a function of distance from the center for a uniform current, right? So you're going to get a magnetic field that's going to look like this.
For 31, right? Which one is this? Which one is this?
This one is the wire with the cutout.
No, that's, you don't get a field of the back.
I'm not done yet. I've just started.
Just
for a wire,
Oh, fair enough.
it looks like this.
I know, it's not
Those vectors are supposed to get longer as you go around, right? So that's the field for just the wire with no cutout, all right? Now I create a cutout. And the field for the cutouts is going to look like this. Now you need to add the two together, all right? So you use Ampere's law for this. I'll need a name. So Ampere's law for this to get the field as a function of distance from the center, all right? And you use Ampere's law for that. Now, for each of those, I probably want to do this right. I can tell you, let's say, I'll just tell you one of them. So we're here, and we go out some distance from the center, right? At some angle phi. Oh, I'll do it in theta, right? No, this is phi, right? And I guess we measure phi. I'll do it this way. I'll measure phi from here, just to be consistent with polar coordinates, all right? The magnetic field then is, I'll even tell you this one if you work it out. 2I over C, distance from the center over radius of the whole thing. So this distance is R, right? R squared, phi hat for current coming out of the board. Yeah.
That's for a current density of
I.
or pi r squared.
Yeah, so you're going to have to, I'm not going to fix that. I'm not going to tell you how to do that. You have to make some correction for a current of I flowing into an area that's somewhat less than pi capital R squared. Right? So your current density is going to be a little bit different. But to me, that's not a big idea.
It's not, but I wanted to note to everyone that that's...
Yeah, so there's got to be a correction for the fractional area. All right? So that's what the magnetic field looks like. I'm going to write this slightly differently in order to help you with the subtraction of that, but I'm not going to actually do that. This actually is 2I over C R over R squared. Phi is actually R cross C. Okay. That could be useful if you think about the magnetic field for the missing section.
It's in the Z direction. It's in the Z direction.
That's the distance from the center of R prime, okay? R prime at cross C. and I'll give you one more thing. If this is the vector from here to here, let's call that vector h. There to the center of that one. Then r prime is equal to r minus h. That's all I'm going to tell you.
That's everything but what Amy's current density was right.
Where big R is the radius of the whole thing.
Oh, big R is the radius of this thing, and
And little
big R prime is the radius of this thing.
Little R prime.
It's a lot nicer than the geometry.
This is, once you do it, and you see the answer. Did it give you the answer?
Yeah, that's
Yeah.
wrong.
Yeah, well, the answer is wrong in magnitude, but correct in spirit.
So he gets 89.
That sounds like all of mine.
Yeah. I'll just tell you that what you're going to end up finding out is that the magnetic field in this cavity is a constant and points in one direction.
That's ridiculous.
And that's just weird. That circulating field minus that circulating field is constant. I didn't look at it, I just did mine.
Does it have any relationship to polarized light?
Oh, you know what? I cheated. Yes. I said, I don't care, it's the corrected current density, you can do as you wish, so I just had I sub C.
The little r's are arbitrary vectors somewhere in between the center and big R, right?
Yeah.
Okay.
In here. So in the cavity, it's this minus that. Very pretty.
Is this kind of like how we can get polarized light from two circulating, or linear polarized light from two
No.
circulating?
But
I was wondering if that was.
a polarized light from two circulating polarizations is really easy.
Okay.
Okay? Because you have polarization that's circulating like this in time,
Right.
and then you have polarization that's circulating like this in time,
Right.
and then now I look at the sum of the two.
Yeah.
And right now it points that way,
That's
now it points that way. Ends up being yes.
That's interesting.
I like teaching algebras. I can do all sorts of dances.
Disco! Does that say B sub INS?
This actually is linearly polarized light 45 degrees. Was that camera on?
Yes.
Yes.
Gum Gum pretends, Disco pretends.
Okay,
That B
I
sub
will have to add a
INS.
subtitle to this.
I'm not
one.
telling you any more here.
No.
Ryan thinks I gave away the whole game.
No, the symbols for the second key.
But we still have to do the vectors though.
Is it an N?
Yeah, you have to, right. And it's really hard.
Let's take it across.
Like this.
Okay, anyone else who comes in later has to go to the video.
I'm sure people will be doing that anyways.
Okay. That was the hard one, I think.
I think that.
Oh, no, taking four derivatives and showing that the derivative's not zero, that's the hard one.
Yeah.
I'll show you my solution, it's actually pretty short.
I wasted an entire day of vacation doing that.
I'm missing a page. Or not, let's see. No, I'm not missing a page. My solution just goes from here to here. What the last line says, other derivatives get messier and are left as an exercise for the student. I did the first derivative and showed it was zero.
Yes, that's very good. We can't write that.
You said in the
Yeah.
email you want us to use Maple or Mathematica and plot it, or do you just want us to use?
I would like you to plot it.
Do I have to plot it?
Okay.
No, okay. If you actually succeeded in taking the derivatives in algebraic form, you know, and you did it, then I'm going to be suitably impressed, and you don't have to plot. But if you use Maple or Mathematica to do the rest of the derivatives, to do any of the derivatives, because even the first derivative is messy, if you do, then you might as well plot it.
What about those
It's
others?
really easy to plot.
Don't-
And then you
yeah.
can look at it and say, oh, look, the field this, that.
What about those of us who don't know how to use Maple or Mathematica?
That's the point of my asking you to do it. I get complaints from upper level faculty and faculty teaching graduate classes where they say students don't know how to do simple Mathematica or Maple calculations and plot the results. So I said, fine, I'll just ask the students to do more of that in my class. I add it to the rubric for your grade.
Add it to the requirements of the physics program. That's a simple solution.
Well, no, it isn't. The problem is that we have a limited number of credits that we're allowed to require of you. And we filled up all those credits with the things that we made the highest priority. So what we decided was that we're going to add computational and plotting things to all the courses. So that you pick it up by osmosis as you go along.
Make the plots on those courses highly recommended.
It is highly recommended.
Okay.
Yes.
Why are we at the limit? The engineers maxed out at 132, but we're only doing 128.
What about engineers?
Yes, actually that is the answer. The School of Science decided that they want to comply with most of the BS in science degrees around the East Coast, which have, and maybe other elite programs across the country. We want to have more or less the same level of requirements. And as you go around and sample the universities that we want to, that we aspire to be like, they have 124 credits for their Bachelor of Science degree. And some of them actually have extremely low named requirements. So we actually, and I voted against this, but I lost, set a limit in like 1992 or something like that, that we would have no more than 40 credits of required work in named courses in the department. And so that's 10 courses. In fact, we've gone one course over that. But that's because, actually, to be honest, about, so we did this maybe 15, 20 years ago. About 10 years ago, a group of us argued to the School of Science that this was unworkable and that we needed to be allowed to require more credits.
You could add in, you know, like we have first semester seminar thing.
Yeah, that's not required.
Is that still running?
You could do
Yeah,
list
okay.
on physics and mathematics like the list.
Yes.
And set the info is on the list required, the list is not required.
Yes. You see, Professor Napolitano only started offering that course 2 years ago. So this, I think, is the third, next semester will be the third time it's offered, at which point we have to make it an official course or we have to change its name. Actually, we did change its name, didn't we? Yeah, the first time he taught it was physics with Maple and MATLAB. And then it became physics with Mathematica and MATLAB. And I think the next time it's being offered is physics with Mathematica.
Yeah. MATLAB's being pulled out.
I don't actually know.
Well, I remember
I think he
talking
changed the
about it
title.
in class.
Okay.
That he wanted to focus on.
Physics. Physics. This side of the room is physics.
Number 29.
Okay. You got the hints.
Yeah.
Yeah.
Well, I kind of started it, so
You need those hints.
yes.
And then you need one more thing. You need the law of cosines, right?
You're doing it geometrically. You could have used the law of cosines. I might just,
Even for that, I think you need the law of cosines.
which one?
For this approach.
Yeah, because
Also, we're supposed to
I mean,
do.
I might redraw.
The answer in the back is the direction is correct, and the magnitude is off by a geometric factor that has to do with the relative areas of this and that. Okay.
That's where it's supposed to be.
He did what I did, actually. What I said was, well, I don't really care what the actual current density is.
Yeah.
I'm just going to say, I'm going to treat this problem as though I have a current I sub c in the region that remains, and then I have the same current density
Yeah,
there.
okay.
Yeah.
in what terms do you want the solution to be? Just r prime r. I guess.
Let me see. The solution should include 2 C R
It's not going to help you here.
R prime
How you just looking at things that should have been somewhere in a solution.
H
Vector.
What base is in the vector of that line?
Z hat. No, actually, by the time I'm done with it, it's a vector.
I mean, it's always meant it's X.
The final answer.
Can I just use H hat?
Okay, the final answer was like this. A constant. H times a direction. This is the direction. I think that's it.
No I.
I mean,
Oh.
that's confusing because you could also answer without
Without this.
you can answer without. Yeah.
Yes. So I'll just put it here. How about that?
Yeah, so it could be.
That's another way you could write it as the magnitude of h times some vector. That vector might be. So you should be able to reduce it to a single expression that includes all of that. And Ohanian messed up a little on the scaling. I think he scaled the wrong way.
I've already expected what I wrote.
Oh. Technically, then we're your direction.
From now on, whenever I write H, I'm just going to start writing H bars.
Yeah, it comes out
Yeah,
as
you get
H
to
plus C.
that is technically then more general because mine's only for below.
Yeah. But so it works generally with that.
Okay, fair enough.
Question about
Should
29.
I rewrite that?
29. Yeah. No, you don't have to rewrite it. 29. Okay. Square loop.
So the way I tried doing it last night was using Biot's Sparks law and then separating it into 4 separate line integrals and integrating. And I don't remember how to parameterize.
You don't remember how to what?
Parameterize.
So let's see. You want to find, you've got something of length, I don't remember what
It is L, yeah.
Yeah.
All right, and you need to look at this edge on. So now I'm going to take this and turn it edge on. There's my wire, and there's the point that I'm interested in. Sorry, my wire goes that way. Yeah, I could put the point at any angle, but
Yeah.
let me actually put it here. All right. So that's because this could be anywhere on this axis. So we have our square, and we want to determine the magnetic field along that axis at the center of the square. Right? So looking at this edge on, all right, this would be my square. Oops, sorry, wrong way. This would be my square, and then looking at it edge on, I'm looking at it like that, right? So it's this far, yeah, no, that's right. This far from the center of the square, but this far from the corners, from that line.
Okay.
All right. So what's important for calculating the field out here is that you need to know that distance.
Okay.
And this is L over 2, and this is the distance along from the center of the square, which might be Z.
Okay.
All right. I won't do that for you.
Okay.
So now you can figure out what that field is. Let's say the current's going this way, and then if I look at that, and that current's going that way. That gives rise to a magnetic field that points that way. Okay. Right? Now, when I add in the other sides, so here's a side over here. That one's going to give me a magnetic field that points that way. Did I do that right? Yes. No.
Wait, which one makes the?
This guy here. Oh, yeah, sorry. It goes this way.
Yeah.
This way.
That opposite.
Right? And the result is that the magnetic field in this case points in the z direction. Minus z, whether I just drew it. What is the current? So you have to be sure when you add the sides that you're adding the components the right way.
Okay.
So you know the field, you know the angle, because you know everything here. You know what the component along the z-axis is.
Done.
Done.
Okay.
Multiply by 4.
Wouldn't
Make
it be
copies.
wouldn't it be by 2?
By having
Wouldn't it be 0?
He got it.
Wouldn't you multiply by 2? Or-
You have 4 wires.
Yeah, but you use 2 wires to compute that B.
Well, there's
That B.
Because H is just.
I use these 2 wires to cancel that. Right. And then I have the other 2.
Yeah, that's what I'm saying. What is
Yeah.
the H vector?
It means that you have 8 identical segments.
Negative 0.
4.
Okay, yeah.
0
So that-
elements.
Oh.
0, 0, 1.
Okay. But that's going to sound easier.
Yeah.
So you get negative.
So each time is 4 or down?
As long as, yeah, I'm trying to think of the positive and negative that is.
You're going to have to
The
count.
main thing is that the H vector in this part is just the
That's too hard.
I think the positive and negative because it just
Yeah.
depends on how you
If it's less than 10,
You know, I ran.
you should be able to do it.
You know, I ran track in high school, and
Because
I
the
always
main point is
did
that it's
the 2 miles, which is 8 laps.
It's-
I always finished at
Did you
7
just say
laps because I couldn't count to 8.
given magnetic field and cavity,
always skip
for
one.
your exterior H
I
vector.
don't know which one I skipped. What
So
I skipped
regardless of
what?
how you find it, that's what finally is. 'Cause that way if you
That's
put
just
it
wishful
anywhere,
thinking.
Wouldn't they tell
Essentially
you?
fine.
It was not actually happened.
So if I just give you 2 I equals 2 S squared, with your I being the
Right.
that's not a correct answer.
I never did anything longer than
So you get obviously the current right?
to get to. Yeah.
Yeah.
Oh, you're right.
So I said, and then there's correction for this and your route is wrong. So there's a route and a route. My vectors.
It's not gonna be hard, it's gonna be actual physics. I don't even like that. This is making it too easy, it's like she's like, but mine is still getting home. Alright. Well, actually, no. You have to know that you.
Yeah, I also.
I don't know. I actually don't know. I'm sorry. Probably not. You have to know to keep reading. Nope. No, you don't have to keep reading. I still know that. You should know that you didn't know. That you didn't know.
I should tell you, by the way, I've never used Mathematica, so I cannot help you at all with Mathematica. MATLAB and Maple, I'm okay, just so stupid. We
I
didn't
won't
have,
even comment on that, on that thing.
we didn't have a Mathematica license here until last year, or maybe the year before last.
No, I'm not talking about Mathematica. I mean when you said you're good with MATLAB.
Oh,
Oh, now.
I am capable of commenting on MATLAB code.
Right? It doesn't involve cell arrays.
Oh, no, cell arrays, no. No cell arrays.
No, I am. Just have Steve do it for you. That's what he did. He do it for him.
Right.
That's the easy way. Just take, you're doing MATLAB design.
So I would use
Is that thing still on?
Yes.
So I would use
You want to turn it off now?
I would use Biot's large slot to find